a physical property. Brandon's table, give me an example of a physical property.
Color.
Color is a good example of physical property. Mikado's table. Conductivity. That's pretty dang good. That's not one that people usually remember. Isabella's area. Alright, sorry, Isabella. Boiling point. Okay, so boiling point, I'm going to go freezing point, and what's the other point? Melting point is the opposite of freezing point. What's the opposite of boiling point? When you go, so opposite, boiling is going from liquid to gas, so what's the opposite? Condensation point. I know you usually don't think about that, but that's something that you could also describe. Alright, so there's a lot of information we can talk about physical properties. So why are we going back to physical properties now? Basically what you learned about would be intermolecular forces, so your hydrogen bonding were the other ones. Dipole, and so I said hydrogen bonding, dipole, and line dispersion forces. All of those create all the physical properties, the variations of the physical properties that we've already described. So we have things with low boiling point, medium boiling points, and high boiling points. And so we need to discuss why the IMFs, the intermolecular forces that we're speaking of, play a role. So as an example, we're going to talk about phase change. So let's do solid to liquid to gas. See if any of that was recorded. Possible? No. Okay, so solid, okay, to liquid to gas. All right, so let's talk about that phase change here. So whenever you're drawing out water, how are you drawing water pre-melting? Yeah. So trying to keep it the particles really close together. Maybe a structure that's a crystalline structure. Maybe don't say lattice because this is not a metal or an ionic compound. We usually reserve the word lattice for that. So I'm going to draw. I really don't want to restart this program. Just doing it until it hates me more. Okay, so this is actually water. Okay, all right, so this is water in ice form. Very structured, very, it's got like a hexagonal pattern. What's in the middle of this? Great, nothing. Good job, guys. Okay, so nothing's in the middle of this. Why is that important? What feature does that portray about ice? It's not as dense, so it floats, right? So that's just a property we kind of know about water. I mean about ice, solid water, which is ice. So what am I drawing here? I'm actually not, I really think I should probably portray that as dashes instead. I'm not sure what the blue wheel of death is going to do, but we're going to keep trying to go. So I'm going to draw dashes there instead between the water molecules, and I'm indicating an IMF. What intermolecular force do you think that one is? That is hydrogen bonding. So is hydrogen bonding really a bond? No, it's still an attraction, okay? So it's just an attraction between a polar molecule. That polar molecule has to have H bonded to what three different particles, or three different atom types? Hydrogen can be bonded to fluorine, oxygen, or nitrogen. So I like to say hydrogen bonds are fun. They're real fun. Okay, so hydrogen bonds are fun. I really try to help you out with the stupidity, okay? It sinks in better. Okay, so we have the ice. We're now melting. So as we melt, what happens? Okay, so it gets flowy. It's a liquid, right? So it spreads out. But what here is different? Sophie. Okay, so maybe they'll move around, so now the gap here is not there anymore. But is my water still water? Yes. Have I changed chemicals?
No.
No, it's still water. It's just now it's floating around in like kind of a blob shape. Okay, so it's blobbing up, so blob. Okay, is it still attracted to each other? Somewhat. Okay, so I really did a hard attraction there. Really good attraction. So now they're just going to like, yeah, meh. A little traction there, a little traction there, a little traction, a little traction. Okay, but it's more flowy. So that flowy is now our liquid form, but it's still attracted via hydrogen bonding because that's what water can do with other water molecules. Okay, so then you can see basically this was supposed to be really, really condensed together. So let me use a different word. Compacted together. This was a really compact structure. This was more flowy. Now you can imagine as we go to vaporization, so as we vaporize it or boil it, what's it going to look like? So really, really far apart, but still water, right? Because did we change the structure? Did we change the chemical composition? Did we? No, it's just phase change. We're not changing the chemical composition. We're just changing how close the particles are together and the strength of the attractions between them. So of these, this one might have a little bit of an attraction, maybe, but probably not because they're so far apart. Intermolecular forces are going to happen when they're very close together, which creates our solid and liquids. Gas particles, they're going to be very, very spread apart, and so they have minimal attractions with each other. So this is how I'm changing phase. I'm overcoming the strength of the hydrogen bond. Very strong hydrogen bonds, really close together, high attraction for each other, high attraction for other molecules. As I heat them up, the particles are moving faster. So as they're moving faster, they have the ability to start to move apart from each other because they're overcoming the attractions they have for other water molecules. And then I heat them up even more, and so they're moving even faster. And so they're like, peace out, bye. And they totally separate from each other in that fashion of overcoming intermolecular forces, aka the hydrogen bond that's in this case. So what does this look like to you? So I know it's not winter anymore, though we want it to be. You go to Panera, you scoop out your spoon. What do you first do with your soup? Okay, most people, it's steaming, right? You just pop the thing in your mouth. Woo! Challenge accepted, go. So most of the time you're probably going to blow on it, and the steam goes away, okay? You're blowing away the steam particles, which are the fastest moving particles, which are the hottest of them. Ice, slow moving particles, cold. Liquid water, slowish moving particles, coldish. Steam, really fast moving particles, hot as can be, will burn your tongue, right? So that kind of gives you information that you already kind of know, but that's what I mean by fast moving particles. It just means they're really, really warm. They have high kinetic energy. Okay, so I just gave you a lot of kind of visuals there. When you're on my website now, because you're on my website, right? Right, okay. I want to give you some time to kind of absorb more information about intermolecular forces before I dive into drawing them more in depth with you guys. So it's called, let's see if my computer wants to function. Oh, well, I don't know where that came from. Okay. So, website. So my computer's not going to work. Okay, got it. Go, go, go. Nope. The mouse just has a mind of its own. So when you're on my, there it is. Okay, so when you're on my website, go to Honors Chem, under homework. I just put classwork down there for today. So you're here, and I want you guys to work. It says Intermolecular Forces Interactive Warm-Up. I want you guys to work with one other person. You guys can make a combined paper with your answers, that's fine. But one person can pull up the doc, one person can pull up the simulation. It's a really, really good way to see the intermolecular forces, because we can't see them, right? I have to draw them for you. And when you go to this link here, it has you go through attractive forces and how does it relate to boiling point. And as you go, it's going to say like drag molecules. So you'll select a pair as it describes in the simulation itself, and you'll drag this molecule. Oops. You'll drag this. Oops. Okay. You'll drag this molecule as it says to. Ooh. I didn't know I could move stuff like this. Look, guys. There's my worksheet. And there's the simulation. Okay. So that's what you guys are doing right now. Okay. So I'm going to give you guys about 25 minutes. Let's see where we are. The worksheet, the link that pulls up. Inside the worksheet, there's an actual simulation. And spread out. Work with people. Go. Learn and make progress. Learn and make progress.
not gonna give you a piece.
Okay. One person can write as you so desire. It's really helpful to have.
Hey. Megan, I'm very disappointed in you. I'm disappointed in you.
You can have one other partner, or you can work by yourself. It does not tell us what you have to do.
It's in solid state. It looks good to have really high attention.
Yeah. Hey, what do you want to do? This simulation or what do you?
So if they're already like attracted to each other, this is
Where's the simulation?
it's solid.
Oh.
It's not right.
Like, this is hard for you to say. Now, predict how difficult it will be to pull apart the molecules in the net. Again, I pulled it apart and it's easy to pull apart. I didn't predict, but polar or non-polar.
So for
No, I think it's polar or non-polar.
2, 1. Okay, because I have one more part I want you to get to on here. Okay, so you're here. You guys predicted your BR. So between your bromines, bromine to bromine, what kind of molecule is that? I was up here. Non-polar, because it's the same. It's a diatomic molecule. It's got the same electronegativity. It's evenly distributed. If you drew your Lewis dot structure out, it'd be bromine with lone pairs all around it. That would be a non-polar molecule. So that nonpolar molecule attracts to the other nonpolar molecule through what weak intermolecular force? London dispersion, okay? So London dispersion force. And London dispersion forces are present in nonpolar interactions, but they're also present in every single interaction. They're just not the predominant force. They're not the main force. But they're still present in everything. So if you're getting to the point where you're like, well, I don't know what force it is, London dispersion is a go-to easy one. So when you get down to HBr, and you think about if you had to draw HBr, how would it look? You have an H bonded to a Br, you have your lone pairs out here, And if you had to assign a partial negative and partial positive, where would you assign your partial positive? On the hydrogen. And then where would you assign your partial negative? On the bromine. If you lined up two HBRs right next to each other like that, partial positive and partial negative, where would the attraction be? Between between bromine on this guy and hydrogen on the other guy. Okay, so your attraction's between the molecules. What's that attraction called? Dipole-dipole, because one, it's a polar molecule. But is it the hydrogen bonding form of the polar molecule?
No, it's hydrogen.
Because hydrogen bonds are bond. It's not F, O, or N, so it's just bromine. So that's why we would say HBr would be a polar molecule interaction. We put dipole-dipole there. So London dispersion is the weakest of the intermolecular forces. That's why it was easy to pull apart. Dipole-dipole is the medium to high intermolecular force. So it was probably a little harder to pull apart. Did we have any examples of hydrogen bonding on that first example? No. So we didn't see any stronger than dipole-dipole. So I want you guys to continue. I want you to drop down to, hold on. Oops. Where it says boiling point, okay? So go to question 3 right now. Try to classify based on your knowledge, and then you're going to go to boiling point next, because this is the part I need you to see before we talk, okay? So I'm going to give you guys 10 minutes to finish up where you can. Start on number 3. Yep, and go down. Start on number 3. Where my timer is.
Hydrogen and fluorine. That would be hydrogen because and that'd be a strong or hard. I don't know what that would be. So you can work with food. Yes, that's fine. And then DR2 and H. I know it's a full molecule, but I don't know if it'd be stronger for nuclear bonding. So if it's polar, that'd be dipole. Oh yeah, it is like this because it's is it not? Yeah, that's what I was thinking about. Explain their line and classification, taking into account their. So what makes this engine pretty how would you expect H of the boiling point to compare to H minus 20? Okay. How good is it? Okay. How I do it?
You know what? Four, that's how many? 7, and hydrogen 1. 3, 4, 5, 6, 7. Accurate. 3, 4, 5, 6, 7. Sure. Okay.
I'm just speeding them up right now.
What are they with another one?
I don't know. But the white pair are going everywhere, and the other pair like staying intact, but they're still moving around. Moving along, but they're staying partially. But they're cool.
You're at 2 HF?
Cooling just went back to because we have fluorine and bromine in the same like group and higher than
Each one has a different attraction. But it's still something we can hold out. Anyway, so yeah, make sure you got any answer this. So HS boiling point.
So tell us anything about what molecule it is. Just say that non-polar molecules that are
Oh, I don't know what the
exactly.
It's just comparing. What's the bond? Which one is stronger?
so we just have to figure out what one now for my bullet.
Stronger higher.
Oh yeah, because it's gonna end up with hydrogen having nitrogen. So when they have the same molecule.
Yeah, and this would have the same or similar.
Yeah. That's one. That's what just explains that because they
No. Yeah. Polar molecules, dipolar. Oh. Like, why you say easy? Because whenever we use yeah. It's gonna be different amounts.
so that's enough. And then after we let it.
All right, guys. When the timer goes off, come back to me.
How long do we have?
You have a minute more to explore. My goal is to keep this point first.
So they have a higher one. Thank you. That makes sense. So HF higher
And the prediction for F and HCl.
we did have like 70 something slides.
What do you want to put the prediction? And then forward. And then that
Alright, come back to me right now. Let's go. So that means that you can sit up. Yep. Getting it up. Abandon your partner and come back to your seats. And then Omar, if you could demonstrate how to walk back up to the front with Caleb. Alright. Omar and Caleb. I don't want to have to fish you out of the pond. Okay. I said, look on the board right now for me, and you guys tell me, the molecules on the right, I'm trying to indicate something. Am I trying to indicate that they are polar or that they are non-polar? The ones on the right. I'm trying to indicate they are polar, showing you the partial positives and partial negatives on each of these, right? And you don't see the partial negatives and partial positives over here. What are you assuming these are? Non-polar, okay? So we got that much. So if I heat this baby up, and I heat it up, oops, I have to start, okay. Heat it up. All right, so you see them moving. You can see the attractions between the particles, and I'm moving, I'm heating them up, I'm heating them up, and I'm heating them up. What happens? The non-polar is what?
Everywhere.
So I overcome the attractions between them, and those attractions are called what? London dispersion forces. So I've overcome the London dispersion forces, but have I overcome really the forces that these are held with? No. Okay, why could I overcome these but not these? Right, so the attraction's really weak. So the weaker the attraction, I heat that thing up, they move apart really quickly. So if I'm heating these up, I mean, I heated it up to 600 Kelvin. What might I have to heat this up to make them overcome their attractions? Say again? More than that, right? 800, 1,000, 2,000 Kelvin, something really high. So which of these would have a higher boiling point? The polar ones, right? Okay, so what's the like extreme of a polar substance? Like, so a molecule that's polar can experience dipole attractions and hydrogen bonding attractions, but that's just a polar molecule where we have a partial positive and a partial negative. What's the most extreme of polar? They actually transfer electrons. Ionic. So remember when we talked about ionic? What did we say about their melting points and boiling points? Like super duper 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 high, right? And so that's going to be trying to indicate even higher than what this is showing here. So now at this point we're going to kind of do a compare and contrast between boiling points or melting points, any kind of those physical points that would be occurring between different types of molecules, and you have to be able to predict these. So let me pause this. Let me cool them back down. They deserve to cool back down. And so as they cool back down, what do you think is happening? They start to slow down. They start to try to condense together again. Okay. So let's talk about this in reference to part 3 of our the links that we started last night. So before I get there, you know the relative differences between the intermolecular forces. We're going to dive into that a little bit more detail, but relative strength differences are what? Tell me the weakest of the intermolecular forces. London dispersion forces is weaker than dipole-dipole, which is weaker than hydrogen bonding. Okay, and so all of these are all intermolecular forces that are within, they're between the molecules, right? But what types of molecules have we been speaking of this whole time? Ionic or covalent? Covalent, right? So these are all covalent molecules. Okay, which of these correlate with polar molecules? Dipole and hydrogen bonding, and this one is non-polar. Okay, so I'm basically showing your chart one more time, just in a different kind of graphic. And so all of these are intermolecular forces between molecules, but these are totally weak compared to true bonds. And what are the two types of true bonds that we've spoken of before all this mess? Ionic bonds and well, I'll say metallic, yeah. And even just simply the actual covalent bond that exists within the molecule. What do you call those within the molecule? Intra. Right, so at this point, yes, true ionic, metallic, and covalent bonds are actually very strong compared to all the intermolecular forces. These are just helping things stay together. Whereas this is like, this atom is bonded to this atom, and there's like no way you're pulling apart unless you put an extreme amount of energy into it. And so, and I actually prioritize them as well. Ionic is the strongest of these. Metallic is really close. It does depend on some other factors, so I'll kind of say they're both at the top. But I'm going to say ionic overall is the strongest of all types of bonds, and covalent comparatively is weaker than sequentially those two as well. So this gives you a good order of operations on how do you approach some of these questions. Okay, so which would have the highest boiling point of everything on the board? Say again? Ionic. Ionic would have the highest boiling point of everything on the board. Then you defer to covalent, because metallic we'll get to on Monday, okay? Oh, speaking of Monday, I think you may be seeing this on my website. What did I say to bring? Pennies, okay. And they're right here. Bring pennies Monday. We're going to make gold. You know, we're just going to do that. So if you could just bring some pennies for me, I can make that happen. All right, so I need pre and post 1983. So all I need is 2 year cents. Okay, that's it. Don't bring in like 10 pennies, okay? So anyway, ionic's the strongest. Metallic we'll talk about more Monday. Covalent's the next strongest, but how do you compare covalent? So you can't just look at a covalent molecule and go, oh, its boiling point is 400, okay? So you have to look at these instead, and that's what we're getting ready to do. So on the sheet that I gave you yesterday where it says Part 3 IMF table, let's talk about this first. I have to actually get to it, I'm sorry. Oh, someone was asking me about hydrogen bondings. There's hydrogen bonding within what? What is this stuff? DNA, right? So there's our hydrogen bond here in yellow, and it's because this hydrogen's bonded to, no, it's not bonded, nitrogen, right? Because hydrogen bonds are bond, so it has to be with the nitrogen. This hydrogen's bonded to a nitrogen, and this bond is bonded to a nitrogen, and yeah, it's hydrogen bonding with the other side of the DNA structure. All right, that's just for fun. Okay, so we did that. And then I have to get to my table. I'm sorry. We have to draw these structures first. Okay, find this table on your sheet that I gave yesterday. Some of you guys have already drawn this. So we are quickly walking through this. Have your electronegativity sheet in front of you as well. Okay? You know what, guys? You draw those first. You draw them. I don't think I need to draw every single one. Just compare them with a friend. Come on.
Yeah.
Alright, you are drawing the structures. If you've already drawn them, please talk to your neighbors.
Hey, don't get carried away.
Guys, don't forget about ionics. They are way different. Do not draw ionics like a covalent.
Oh, bro, we can figure all that out.
I wasn't drawing that. 3.0, 2.1.
Oh, the bracket? Yeah, and then the ionic. You just like, so, let's say like you have sodium and like chlorine. Let's say that, you know how like sodium has to give chlorine one to become like octet? So you would do like minus plus 1 under like beta.
That was Cassandra. That was only for one of those examples. It was only because you were doing 2 different types of molecules.
In it,
Yes.
so like and then outside of it, you
Yes.
just put minus 1
Yes.
because it's got and what? Yeah. Yeah, as I said, it's kind of easy. But you just like come here to like find out what one it is.
No, it's full negative, full positive. There's no
To
partial.
find out what one it is, you just like.
I'm going to talk about that in a second. There's that one. Because when you hear the word molecule, molecule means a molecule, like covalently bound molecule. Ionics we don't really call molecules, so that word helps to see there's actually not a force that we speak of as an ion. They're just compounds. Okay. All right, you should be done very soon. Yes.
Like, how do you know if it's choosing or
Guys, eyes back up here. You've drawn these structures a number of times between prom set, and a lot of these are, I think, identical to what was in your lab, except for some of the ionic ones. So let's start with number 1. This is ammonia. NH3 has 8 valence electrons. You gave everybody bonds, and then you gave it a lone pair. Let's decide right now, what is the geometry of this? Molecular geometry. Shape. If you need to use your shape sheet, use your shape sheet. Can I get more than one person to help me out? Trigonal pyramidal. Okay, so trigonal pyramidal. So think about that, visualize that. Your head is the lone pair. You've got your legs pointing down. Is there an equal or unequal distribution of electrons? Say again? Unequal. Why? Yeah, you've got this huge lone pair up here, which is partially negative, right? And then a lack of lone pairs down here, which is partially positive. Okay, so you're with me? Unequal distribution, is that polar or nonpolar? That is polar. Okay, so put polar here for molecular polarity. And then this is where you just figured out some of your intermolecular forces. Polar molecules experience what 2 possible IMFs? Dipole-dipole or hydrogen bonding. Okay, so you can see that it's going to be dipole-dipole or hydrogen bonding because of this polar molecule. Then you backtrack. It has a hydrogen bonded to a nitrogen. And that's a part of the category for bond, okay, so which is hydrogen bonding. So basically from the polarity, you're looking at, does it have dipole-dipole, or is it hydrogen bonding, and you classify it based on the bond that's here, which is nitrogen and hydrogen. And since it does have that, the hydrogen bonding rules, that is our IMF there. We'll look at our comparative boiling point after we have the whole chart done. That is what I want you to do right now. Determine the shape right here, determine the molecular polarity, and then IMF. I'm saving my 2 ionics to talk about at the end. And I'll tell you now, you should be identifying metals and nonmetals as ionic, and I want you to draw them like you know you should. Okay, so take a couple more minutes there. I'll have some instructions on the board for you.
how long does it
Magnesium would have 2. So chlorine overall would have 2. Yeah.
I'm not highlighting it right now, but we really have to do it.
Do you ever have a non-metallic ionic surface? What I do with like
Wait, if you have energy and it loses to
Guys, how do you draw an ionic fluid structure? One more time. So you transfer the electrons, and you put brackets, and you put plus or minus charges. Ionics are very special. You're not actually physically bonding together.
Well, what? No, they have to be a metal amount. It's prevailing, like, not metal amount.
Are you bringing everybody to the office?
Oh. So this one is ion. Yeah. So magnesium is equal to 2. And fluorine is equal to 2. So you digest this is the ionic diagram. See, fluorine is only, they don't need
All right, come back to me. Let me answer some more questions. 5, 4, 3, 2, 1. Eyes up. Okay. So I had some more questions about what is the difference between bond polarity and molecular polarity. I know you're hearing the word polarity. You're like, oh, it's the same thing, whatever. No, bond polarity is between this nitrogen and this hydrogen. Who is getting the better share of that 2 electron bond?
nitrogen.
Why nitrogen? Because it has a higher electronegativity. How do you know that? Okay, so you can do this, and it's farther to the up and right, or you can look on your electronegativity sheet, and it says something higher than 2.1. So many times we were drawing our arrows to push the electrons in towards nitrogen. I'm trying not to like junk up these figures too much because it gets kind of messy, but I think you'll be okay if you remember to think about that. But that's where we're looking at the structure and the geometry to figure out the molecular polarity. So go down to water, H2O. What is the shape that this took on? And I kind of drew it that way, but you should be able to look at your sheet as well. Shape. Bent, because our 2 lone pairs are up high, and what are they doing to the bonds? They're pushing, they're repelling. So this is bent. So visualize that. You're thinking about kind of where's everything out? What's on the top? Partial what? Partial negative on the bottom. So polar, non-polar. Polar because it has, what's our word? Equal or unequal? Unequal distribution of charge, right? One side has more electrons than the other. So it's polar. So then you have to consider polar has dipole-dipole or hydrogen bonding. What does this case have? Because H is bonded to oxygen, okay? So it can't hydrogen bond with another water molecule if we wanted it to. And remember, we're talking about between the molecules, not necessarily those hydrogens, but between the molecules, that's where a hydrogen bond occurs. All right, so it's polar, it experiences hydrogen bonding. Okay. CF4, shape. Tetrahedral, and you're not memorizing these unless you want to, but you have a sheet in front of you. How many ligands are here? 4 ligands. How many lone pair on my carbon? 0. So on your sheet, that's correlating with tetrahedral. Okay, so think about how is it arranged. Is it in a flat T like this? No, I'm talking 3D. How's it actually? It's like this, something like that, right? Okay. So we know that it's got a 3D shape. My fluorines are all pushing the electrons out, polar, non-polar. Non-polar, because all the way around here, there's an equal distribution of fluorines, equal distribution of charge. Yes, ma'am.
So for the NH, the needle node, the intra ones are
Polar covalent.
you to look at the lone pair there.
Because they're all pushing their electrons towards nitrogen, and then there's a huge lone pair, so they're pushing even higher to make a severe negative on the top and then partially positive on the
So
bottom.
if we didn't have a lone pair, it would be
perfect, yeah. So trigonal planar for that would be nonpolar, but because of the pyramidal shape, it forced it to be polar. Yep. The geometry is super duper important. So you guys said this was what? Nonpolar. Okay, so if it's nonpolar, what's the only force it can experience? London dispersion forces. Okay. Now we get down to magnesium chloride. Ionic, covalent, metallic, what? Ionic, so you draw them very differently, right? So I've got my two valence electrons on magnesium, and I have one, so I have 7 valence electrons in chlorine, but I have 2 of them. So there's 2 empty spots, basically. One on one chlorine, one on the other. What's happening? So we're transferring electrons, and so then what does the whole structure look like in the end? Mg with a charge of 2 plus because it lost 2 electrons in chlorine with a negative 1 charge. It does not have an intermolecular force. The word molecular means covalent. It means a molecule that's a non-metal. So we will not have anything there. We will just put ionic for now to make sure that you're clear there. Yes, ma'am.
Do you still need like the subscript, or do you need to draw two lines?
You can either draw, you can either draw 2 chlorines or put a subscript there to represent there are 2 of those negatively charged particles. Caleb and Lauren, focus. Okay, so now you're at PCl3. PCl3 has what shape? So we have 3 ligands and we have a lone pair. Trigonal pyramidal, right? That lone pair creates some pushing down of the bonded pairs to create a trigonal pyramid. Okay, so that pyramid has a lone pair on top, partial negative on the bottoms, not as negative. I know it does have lone pairs, but not as much as just a single lone pair on the top, tippy top. Polar, non-polar. Okay, so this is partial negative right here, and this is not as partial negative, so I'm just going to say not as partial negative. Okay, so there is an unequal, despite it being partial negative, in most places it's not as partial negative, so it's going to be polar because it's an unequal distribution of charge. So, what kind of intermolecular force could this have? Why not hydrogen bonding? Because there is no hydrogen bonded to F, O, or N. It's not just does it have hydrogen. I could have P with 3 H's and it still would be dipole-dipole. Okay? And then we have nitrogen. This was on your structures from yesterday. Look at it. What's the shape? Linear. Okay? The more you guys participate with me, the better you'll feel about this, okay? Because you're on your own for the last part of this. So this is linear. Okay? So it's on both sides, partial negative, partial negative. What would you guys say about polarity? Non-polar because it's equal on both sides. So if you're non-polar, what IMF do you have? London dispersion forces. Almost done. Last one. Non-metal and metal come together to make what kind of structure? Ionic. So then how do we show this process? Sodium transfers 1 electron to chlorine to make what? 1 plus and one. Okay, and we don't need a thing here because it's not it's ionic. It's not going to be a molecule at all, so we wouldn't say it has an intermolecular force. Okay, so this is all old material now, so we've done enough of this to feel comfortable. The boiling point comparison is really the only part that's new today that has a lot to do with all the intermolecular forces. So let's order this from the highest boiling point to the lowest boiling point based on the force of attraction. What type of bond has the highest boiling point? Ionic. But we have 2 ionics here, right? So I told you before on how we compare ionics, okay? So ionic, you have to compare something called charge product. What does charge product mean again? So the product, the numerical multiplied product. So charge product means multiply the charges. Of these, what's my charges? I see positive 1 and negative 1. So what's the charge product there? Well, just assume absolute value, okay? So this is 1 when I compared 1 and 1. What's my charge product of my other ionic? 2, okay? Who has a stronger attraction? Magnesium chloride versus sodium chloride. All ionics are called salt, so salt's not too specific. You mean table salt if you're going to say that. So this is number 1. This has the highest boiling point. Write that down. So then who's my second highest boiling point? The other ionics. So this is how you're comparing ionics. Okay, so do you have any other ionics to compare? No. Okay, so now we are out of ionic world. We're going to covalent world. How do you compare the covalence, which has the highest boiling point? Something with hydrogen bonding. Okay, so we have how many with hydrogen bonding here? 2. Okay, so these 2 right here. So here's what you have to do to compare those. And I skipped this part earlier because I wanted to get to this part first. So what do you have to do to compare these? Okay, right here. So on your little table at the top where you have your London and dipole and hydrogen bonding, write down this right here. Hydrogen bonding, the strength of the hydrogen bond increases as your molecular mass or molar mass or just weight, the mass increases. So write that up here, wherever you have your details of your hydrogen bonding. So that means you have to add up masses and you'll compare them. So check, you've gotten that? Thumbs up? Going back to my examples, because this is all information you already have in your table. I really wish my table was right next to that, but I was not that smart. Okay, so look over here, find nitrogen and find hydrogen on the periodic table. You need to have a blue periodic table in front of you. What's nitrogen's mass? 14. What's hydrogen's mass? So there's 3 of them, so total that 3. So what's the total mass? 17 grams is what we would say that is, or 17 AMUs. Look at water. Periodic table, hydrogen weighs 1, but there's 2 of them, so I'll say 2 overall. Okay, plus oxygen, which weighs 16. What's the total mass? 18. Okay, higher molar mass? Higher. Okay, so water has the higher molar mass, so it has the higher the strength or the larger intermolecular force of hydrogen bonding. So water is going to have the 3rd highest boiling point right after sodium chloride. And then our other hydrogen bonding is going to be number 4. So we've checked ionics off, hydrogen bonding off. So sequentially, what's the next highest boiling point? Dipole. How many of those do we have up here? Only 1 right here, PCl3. So it's automatically going to get number 5. Okay. Yes.
So if we have multiple dipoles, do we just have one?
So that it does follow the same rule as hydrogen bonding. So hydrogen bonding had increases with mass increases, and so does dipole. So write the same thing there for dipole. That's the only other factor that you did not have in your video notes from last night. And I'll go ahead and show you the London's version while I'm here, okay? So this one, London's version, increases as the number of electrons in the compound increases, and I'll tell you why. Write that down under your factoid for London's version. So that sheet is a nice healthy study guide, okay? Hoping that all your notes and your diagrams are there together. Alright, so why electrons? This is what the guy said in the video. Electrons disperse, which means they move. And as they move, they create that temporary dipole moment, which is just really, really minute. It's barely there, but it immediately goes back to nonpolar. And the electron moves, and it's polar for a second, and it goes back to nonpolar. It's instantaneous, and it's gone in a second. So because the electrons are moving and causing that quick attraction, that's where we're counting electrons and not masses like the rest of these. So that's the main difference there. So let's go back to our chart. Give me a thumbs up if you're good. Muchas gracias. Okay. So back here, we had 1 dipole, so that was easy. We just go ahead and just claim that as number 5. And so now we're looking at 2 London dispersion forces, carbon tetrafluoride and nitrogen here. Compare them by looking at the number of electrons. I think it's easy to see. How many electrons are here? Okay, so there are 32 because you counted up your valence electrons before you started drawing your figures. And here there are 10 because nitrogen has 5 each. But you can even look on the structures themselves. You can see there's a ton more electrons here. So who has the stronger London dispersion force? CF4. So this would be number 6, and nitrogen would have to be number 7. All right, so let's think about number 7. You said it has the what boiling point? Lowest boiling point. So like, give me a low boiling point. Give me a number. 20 degrees what? Celsius? Celsius, okay. Room temperature is like 25 degrees Celsius. So what state of matter would this be at room temperature? Hold on. So I just said boiling point, right? Boiling point means you change from liquid to gas, okay? So at 20 degrees Celsius, we said that was a low boiling point. And if we're at room temperature at 25, what state of matter?
Yes.
It would be gas. Oops, sorry, this one. Nitrogen. Duh, right? Think of our atmosphere, guys. What's the predominant part of our atmosphere? Nitrogen. 71% nitrogen. And the most of our atmosphere, it's not liquid and solid hitting us in the face. It's gas. So it makes sense for the weakest forces to not have a lot of attraction, to allow for gases to form. Versus, have you ever seen gaseous sodium chloride? No, you've only seen solid crystals of like table salt. So that makes sense. That's really, really strong attraction. So that's likely going to be a solid most of the time at room temperature because it's so strongly attracted to each other. So I basically did all your homework right now. Let me take a question first. Yeah.
Right, so is that why, like, when you're at the beach and then you see the water evaporating off the ocean and then it rains, it's fresh because the salt stays behind?
Yeah.
It doesn't have a high melting boiling point?
Yeah, because the salt, that's why you feel crusty, right? So the water evaporates off to you, and you feel kind of grimy and salty because the salt does not evaporate with the water. And that's our physical distillation process we talked about, oh gosh, 2 or 3 weeks ago. Yeah.
Can you just explain like how PCl3 is like partially there but not partially there?
Yes. So it's mainly because I don't have my structure drawn like a triangle. So it's like this. Lone pair, chlorine, chlorine, chlorine. Okay, so there's a slight polarity to these to the bonds here, but this is like super duper 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 lone pair with a partial negative because it's alone by itself on a structure at a point, whereas these are kind of spread out some more. So this is a small partial negative, small partial negative, small partial negative compared to the huge partial negative here. So it's still partial negative, but it's not the same magnitude. Okay. All right. Let me pause on questions for 1 minute. Okay. So what I was going to have you guys do was finish up your lab with your last column. Did you guys see that was IMFs? Okay. You need to have that lab 100% done Monday. That means order or write down your IMFs. You guys have 7 minutes right now. Knock that out into groups. Order your IMFs. And label your IMFs and then order them in order of increase in boiling point or decrease. Okay, so I did part 3 basically for you. I was going to have you do some of that for homework, but, we did it together. And Cassandra, what's your question? So your lab sheet right now needs to be done.
What do you do if the shape isn't working?
Yes, I'll rebuild this for here now, actually.
You have 4 of them too. Yeah. Hey, did you know what happens in a regular class?
I already got oxygen, that xenon, tetrafluoride. So xenon with 4 fluorines, I think it's the 4th one. And John. Xenon with 4 You had to sign sheet. This one has 4 sides. Square. It's a flat square. So what? So it's not a sheet. And that's for this one?
And it is rotating in the bottom.
Yes, that's what, so that previous one we didn't have clarity. So this was like equal in all directions, and it was one here, here, they need each other. And what about this one? That's right. Non-polar. Of course, build some more. You guys need to see some. Guys, go ahead and have, go ahead and start putting up your laptops. Alright guys, laptops up for me. I'm answering a couple questions before we go. I'm changing homework right now. We didn't get to that. So. Homework, listen up. Put your laptops up. We're leaving in like 30 seconds. Homework is finish your lab sheet 100%. Finish lab. And at this point, you should be able to finish up everything from problem set 7-8. I did not take that problem set 7-8, so if you were feasting on that last night, you should be done. You might need to go back and look at your line maps, and that's probably about it. So 100% of problem set 7-8. I will change my website later. Oh, that's right. You can see it out. I always just Brandon, you're ridiculous. Bye, Avery. Bye, guys. Have a good